uniform probability space. Okay. And so now we're going to study uniform probability spaces. Before we get going, I just want to, give you a couple of pointer exercises. So exercise 15.9 and 15.10, very important exercises for you to do in the text, and the answers are all there for you to sort of see, the notion, get practice with the notion of a probability space and practice with some of the manipulations that we can do when we're talking about probability spaces. For example, a generalization of the sum rule from counting to a sum rule for probabilities. Okay. So do these two exercises, important. Now we're going to move on to a probability space, the uniform probability space, this is an example. Okay, so in a uniform probability space, the sample space has size, size of omega. So in this case, 4 equals 4. Okay, and the probabilities are all the same. Okay, and so the probabilities are all the same. And in this example equal to 1 over 4, which is by coincidence happens to equal the size 1 over the size of omega. Well, that has to be. Why? Because if the sum of the probabilities is 1, so sum of probabilities equals 1, then the only way that the sum of 4 probabilities can be 1 if they're all equal is if each of them is 1/4. Okay? And that's true in a general uniform probability space. So the sum of the probabilities are 1. Okay, this implies that in general, the probability of an outcome in a uniform probability space is exactly 1 over the size of the probability space. Okay, so then what's the probability of an event? The probability of an event, is exactly equal to the sum of the probabilities for the outcomes in the event. So the outcomes in the event, the sum of the probability of that outcome, which is, that's the definition of the probability of an event. Okay, and if all the probabilities are equal, so this is the sum of outcomes in my event, the probability, 1 over the size of the sample space. Okay, so I'm adding up the 1 over the size of the sample space for each outcome in the event. So I'm going to end up with the number of outcomes in the event times 1 over the sample space size. Okay, so I'm going to box this for uniform probability spaces. The probability of an event is equal to the size of the event divided by the size of the sample space. Okay, so let's take an example. What's the probability that you get at least 1 heads? So the probability of at least 1 heads. Well, we could identify the events. So here's at least 1 heads, here's at least 1 heads, here's at least 1 heads. So we could add these up. 1/4, 1/4, 1/4 gives me 3/4. Okay. The alternative is to just count the number of outcomes in the event. So at least 1 heads corresponds to 1, 2, 3 outcomes. So we take the size of the outcome, the size of the event, 3, divided by the size of the sample space, the number of possible outcomes, 4, and we get the same answer. Now, why is this very convenient? This is very convenient because computing probabilities for a uniform probability space exactly equates to counting the sizes of sets, the size of the event and the size of the sample space. Okay, that's what it equates to, counting the sizes of sets. So let's do an example of that. Okay, an example. Okay, and we asked this question at the beginning. You flip 3 coins. Okay, how many heads? Okay, now we're ready to answer this question. We don't know how many heads, but you could get 0, 1, 2, or 3 heads. But let's approach this from the mechanical probability approach. So the experiment is you flip a coin, so you can either get heads or tails. Now you flip a second coin, you can either get heads or tails. Heads or tails. For the second step in the experiment. Now flip a third coin. You can either get heads or tails. Heads or tails. Heads or tails. Heads or tails. Okay, now let's compute probability. So what are the outcomes? There's H, 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 3 heads, H, H, T. Okay, then there's H, 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 T, H, H, T, T. T, H, H, T, H, T, TTH, TTT. Those are the outcomes. How many outcomes? Well, when you flip 3 coins, you can get all possible sequences of length 3, where these are binary sequences. Binary because they consist of either heads or tails. And we know that there are 2 to the 3 sequences of length 3. So this is the outcome space omega, and the size of the outcome space is 2 to the 3, which equals 8, and we've verified that here. Okay. Now, let's look at the probabilities. So, when you flip a fair coin, now this is where it's important that the coin is fair. Each of these is equally likely and they must add up to, so this is a half-half. Half the time heads, half the time tails for the first toss. So half. Okay, now once you get to the first toss, when you make the second toss, half the time heads, half the time tails. Half. Okay, and when you get to the third toss, half the time heads, half the time tails. Half. And you see all these are going to be 1/2. Okay. So now when we compute the probability, for example, of HHH, we multiply 1/2 of the time, off 1/2 of the time, off 1/2 of the time. So we get 1/8. And you'll see very quickly that it's going to be 1/8 for all of these. So it's a uniform probability space. And no surprise, the probabilities are all 1 over the size of the sample space. Okay. So uniform probability space. Probability space. And so the probability of an outcome, for example, HHH, is equal to 1 over the size of your sample space, which is 1 over 2 cubed, 2 to the 3, which is 1/8. Okay. Now we can ask, what are your chances of getting 2 heads? The chances of 2 heads. Well, in a uniform probability space, it's just the number of outcomes in the event 2 heads. Okay. So the number of sequences of length 3 with 2 heads. The number of binary sequences with 2 heads. That's the same as the number of binary sequences with 2 ones. Okay. So probability of 2 heads equals number of outcomes with 2 heads divided by the size of my sample space. Okay, which is equal to the number of outcomes with 2 heads. Well, that's 3 choose 2 divided by 8. Okay. And you can go and compute that, it's 3/8. But we can now compute the probabilities for all the possible number of heads. So you can have number of heads. Okay. You can either have 0, 1, 2, or 3. Probability. Okay. 3 choose 0. So this would be 3 choose 0. Choose 0 divided by 8. 3 choose 1 divided by 8. 3 choose 2 divided by 8. And 3 choose 3 divided by 8. Okay. Why? Because the size of the event is the number of sequences with 0 heads. The number of sequences with 1 head, that's 3 choose 1. The number of sequences with 2 heads, that's 3 choose 2. And the number of sequences with 3 heads, that's 3 choose 3. This is 1/8, 3/8, 3/8, 1/8. So, we can't answer this question, how many heads you get. But we can tell you what are the possibilities. You can either get 0, 1, 2, or 3 heads. And we can tell you how likely each is. 1/8, 3/8, 3/8, 1/8. So the chances you get 2 heads is 3/8. The chances you get 1 head is 3/8. What that means is that, if you repeat this experiment many times, 3/8 of those repetitions will have 1 head. 3/8 of them will have 2 heads, and so on. Okay. So that's an example of, a uniform probability space. Okay, so exercise. You flip 4 coins. What are the chances of getting 2 heads? So now that's an exercise. And I'm going to, just tell you that the outcomes are, the sequences of length 4, binary sequences of length 4, binary containing heads or tails, and it's a uniform probability space. Okay, now you can sit down and think about that. Okay, but now pause, I'm going to give you a few seconds, 1, 2, 3, 4, 5. Pause the video, okay, and work it out. Okay, 1, 2, 3, 4, 5. Now, okay, if you pause the video and worked it out, or you just want to see the answer, well, we're interested in, the sample space size, is all sequences of length 4. This is 2 to the 4. Okay, and the outcomes with 2 heads, how many are there? There are just 4 choose 2. So 4 choose 2, okay, which is equal to 6 over 2 to the 4, which is equal to 6 over 16, which is equal to 3 over 8. So the chances of 2 heads is 3/8. If you got that, fantastic. If you didn't, okay, sit down and work through it. Okay. And in the text, we show an example of using a uniform probability space to compute things like, the probabilities of various poker hands, like flushes and full houses and so on. So if you're into poker, have a look at that example. Okay, let's erase, and we'll be back.